Hello everyone, welcome to Advanced Verilog Design with FPGA. We are from Logictronics and Digitronics Nepal. So this session is on Verilog Design. So we will talk about Verilog syntax, semantics, different writing styles, and the different modeling styles, and we will talk about different design approaches for combinational and sequential circuits, and we will also go for the conditional statements, loops, and up to the state machine design and few more application based projects. So in each section we will talk about and do the lab session. So let's begin our quiz section. So we are at currently the first lecture, which is value basics. So in this lecture we will talk about basics of or overview of Verilog and lexical convention and syntax. In lecture 2 we have data types, string, vectors, integer, real, etc. Lecture 3 is system tasks and compiler directives. Lecture 4 is data flow modeling. Lecture 5 is behavioral modeling, and lecture 6 is lab session of this first section. So lab 1 So we will do the basic project with Verilog, and we will use the uh, specific tools, that is Xilinx Vivado tool for simulation as well as writing the main project. So let's start with lecture 1. Actually this lecture are not the separate one, so we just continued everything up to lecture 6 in this slide. So we will go from lecture 1 to lecture 6. These are just different segment of this section. So basically you are already familiar with Verilog. Verilog is hardware description language, SDL, mostly termed as SDL. So this SDL are utilized for hardware design, simulation, testing, verification, and implementations. So IEEE is the standardizing body or organization for SDL. So it standardizes SDL, Verilog SDL in uh, 1995. So first revision is released then. So it have the number of 1364 of standardization, and there is also another revision of Verilog, that is 2001, which is basically released in 2001, and there are some other two versions of Verilog, which is 2005 and 2009, while the version of 2009 is merged with system Verilog. So basically system Verilog is the superset of Verilog. So this is the very basics overview. So initially Verilog was developed and now maintained by Accelera. So they have the group of Open Verilog International. So they deal with the updates and like new revisions, and they request for the standardization to IEEE. So basically Verilog is similar to C language, C programming language, and it is heavily preferred hardware design and verification language in the EDA, electronic design and automation sector, and the like VLSI and FPGA and ASIC designing. So many companies in US utilize or prefer the Verilog, while there is another SDL also, that is BSDL, which is also competitive, but Verilog have higher market share than the BSDL, so it is heavily used. So most of the universities also taught this language, and many institutions and the companies use this language for design and verification. So this is the very basics. So here is the Verilog design flow. So we can see from the starting of Verilog code, we do the simulation and we do the synthesis process. So and after the simulation and synthesis completes, there will be have some gate level simulation or the re-simulation. That means simulation can be done in number of steps, because simulation is just the testing of the modules or the algorithm. So then after we will do the implementation design or implement design process. Then the finally, if we want to implement the design on FPGA or the any logic gates or any devices, then we will generate the program file and run that program file on FPGA like devices. FPGA are the like field programmable gate array. They are not a big big thing or separately like a new thing. They are just logic arrays and combination of logic arrays. So same design flow can be explained with this figure. So this is a little bit elaborative. So first of all, requirement has to be identified and it can be written up on RTL model or algorithm or BSDL code, and then we can do the simulation. Then if the simulation gives the best result or the expected results, then we can go for synthesis. So synthesis process is actually the checking of syntax and semantics. So it checks the overall code and it generates the RTL schematic. So after the synthesis process, we can get the schematic of the design. Then we can do the gate level modeling. So however, this process is not done or prefer independently. We just do the synthesis and we can do the simulation again, and we can go for implementation phase where we did place and route and timing model, timing modeling or timing analysis. Then after we can do the general pre-stream, we can follow this step and program the FPGA. So this is the top level payload design flow, SDL design flow. And let's go for next one. So basically there are four different abstraction level on Bedrock. So basically abstraction level is actually how the information can be hide or how the information can be encapsulated in the design. So basically there are four levels. However, most of literature or most of books talks about gate level modeling, data flow and behavioral. So we can see the lowest level of abstraction is provided by switch level abstraction, and the highest level is provided by behavioral or algorithmic level abstraction. So switch level is like utilizing the or implementing the design on transistors, switches, nodes and interconnections, and this is not much like use and talk on. So the second one is gate level or structural level. So basically gate level or structural level use different entities, different like modules, and the main foundation can be of like using the logic gates or logical primitives, which are also called primitives. And the data flow level or RTL level is utilize many designs. So in this level the assign segment is utilized, and some the like logical equations like K-map based equations can be utilized on the data flow level or RTL level. Actually data flow level is also termed as register transfer level modeling. So another is the heavily utilized model, which is behavioral or algorithmic level. So this is like writing any program in the high level language, high level approach, not the language, the approach. So in high level approach, we can utilize some like conditional statements like if else, case, loops, etc. So this behavioral architecture does not need to know about the details of hardware registers or architectures. So it is just like is the other high level language. So basically Verilog is a successor of C language, like derived from C language. So it is like is the C programming language. We can use the behavioral algorithmic level of abstraction. So these are the four abstraction level, while we will talk about data flow and behavioral in this session, in this section first. So here we have the lexical conventions. So as we already talk about the lexical conventions, so it is like the standard practice of writing in Verilog syntax or semantics. So basically we utilize the case sensitive model. So uppercase letter or uppercase variable name is different than lowercase. So Verilog is case sensitive, and like if we define a variable in uppercase manner, then we have to use that same name or same style. And another is how we can write the code like multi-line or single line approach. So it is free format, so we can start from anywhere and we can in the similar manner. So we can like structure our code like this first line, or we can just structure in like this option. So another is comments, Verilog comments. So comments are like the C language, so it can be have double slash or for the single line comments, or we can have slash asterisk and asterisk slash for multi-line comments, and we can also have the nested comments like is here. So nested comments are for comments inside the comments. So we can utilize nested comments for multi-line comments for identifying the like code, or like instructing what is happening in the code. Another is the operators. So operators basics are here. So operators can be like basically three types, which can be differentiated by unary operators, or unary. Another is binary, and another is ternary. So unary operator just need the single operand. So like any operation, or any tags, we can have different number of operand, but unary need single operand. Here we can see this tilted sign is the single um, unary operator with single operand. So another is double AND, which is logical and. This logical AND is the binary operator, and another we have the ternary. So ternary operator is also utilized for like designing multiplexers or demultiplexers. So like what happens in this third line, ternary operation line, is uh, A will get the result of this assignment. If the value of B is true, then A will get C. If the value of B is false, then A will get D. So this is the ternary operation, which we will also talk on next slide. So let's go on the next one. So here are some basics of how the top module can be written up. So in the top module, or the main program of Verilog, the first line is like time scale 1 nanosecond slash 1 picosecond. So this statement or this line defines the timing behavior of the code. So how much time precision or timing primitives, or like, actually this is the timing directive. So how much precision of time we need to use on our program is defined by this line. So it tells the compiler that while we have like a timing control statement in the program, that will have like picosecond of precision. That means we can write up to picosecond of precision of time. So we will also see the example of this compiler directives in next slide. So this is the very basic code for AND gate. So we can see the module is the keyword. So AND gate is the module name. So this is user defined name, and it have three different parameters or the ports. So actually this is Verilog 95 version of code. So this 95 version of code have all the input ports or output ports listed in this first line. Then it is ended with semicolon, and after that line we have some orientation of ports, that is input A, input B, and output Z. So these are the orientations, and we have the operations. Operation is actually done in assignment or assign statement. So assign, the assignment is here. So what happens here is ANDing of A and B will generate the result and gives it to the Z variable, and Z will swap the results. So Z is output port, so it will swap the results, and we have the in module of this program. So this is the very basic 95 version of Verilog program for AND gate. So let's see the simulation test bench for this. Actually, simulation test bench is the next level for generating the waveform or the simulation graphs. So it is used for like verifying the design. So we have write the Verilog code for AND gate. So if we want to like verify the AND gate, then we can write the simulation test bench. Like in the top module, we have the like timing directives. So we have another thing is the impt module declaration. So we have module name is different than the top module. So this is like the top module, and this is simulation test bench. So simulation module is called test bench. So here we have the name of test bench module different than the top module, and we have actually the test bench module don't need to have some ports. It will just have registers. So registers and wires are there. So all the input ports defined in the top module are termed as registers, and the output port is termed as the wire. So this is the very basic standard, and double slash things are already comments, so comments will be rejected or not compiled by the compiler. It is just for the user notification or user information. So another section is we have the UUT section, unit under test, where we call our top module. So if we want to do connect two different modules, then they have to have some connection lines or connecting points. So this is the main connection line. So in this section what we have did is we have UUT. So AND gate is the top module name, so we call this AND gate, which is the top module name. So this AND gate is called here, and the format of UUT, so UUT is standard. So in the bracket we have the and port A of AND gate is connected to register A, port B of AND gate is connected to register B, and port Z of AND gate is connected to register Z. So sorry, wire Z. So here we have the A, B, and Z. So AND gate port are connected with the uh, test bench register wires. So after that we have the stimulus like initial begin, and we have some stimulus is the set of statements where we define or declare or instantiate the values for variables. So we instantiate 0 for a register B, and we have some delay as we talked previously. So this line works for this statement, which is timing control statements. We have hash 100, which is actually 100 nanosecond of delay, because the precision is nanosecond by picosecond, so it keeps the nanosecond delay with picosecond precision. So we have the 00 state of AND gate, 01 state of AND gate with 100 delay, 10 and 11 state of AND gate. So it will generate the waveform for AND gate simulation. So waveform will be like we can also see the waveform in the next slide. So and verify the design. So initial begin has been ended here, so we can see here, and we can go for next one. So here we have an differentiation of Verilog 2001 and 1995. Actually most of our content are using the 95. However, we will also talk about the 2001. So 2001 is much more easier to write because few lines will be reduced there. Only 95 is presented in the slide, but 2001 is like is the 95. Other things are same, just port decoration is different. So we can differentiate things from here. So these four lines are represented by this line up to here, and we have the assign statement is same, and we have the in module, and we have assign statement and in module. So this is the Verilog 2001 and 95 revision. So we have the next section of lexical conventions. So we have some number specification. Numbers can be of size means the specific size can be fixed. So we have example here, 4-bit binary 001. So 001 is the binary value, which is 4-bit, and it defines the binary. 16-bit x d2a is 16-bit x value. So if we want to define any size value variables, so we use this type of standard. So another is on size is like without any size parameter. So on size numbers while simulation it must be size, but one size number can be utilized. So it must be like 32-bit format. So there can have negative numbers, and so numbers can also be separated by underscore. So if we want to have multi-bit numbers, like underscore is separating here. So x and z values are also there. So x is for unknown and z is for high impedance, and extending a number. So if we want to extend any number, so here we have an example. We have register A, and A is 12-bit. So if we want to place the 12-bit hex value, then we can write like this. So it will give xxx to A. Actually x stand for hex value, so hex undefined or unknown value. So let's go for the next one. So we have the string. So string can be like written up in the inverted commas, and some string can be displayed like is here, like is the C programming language, and we have the identifiers. We will talk about display in the next section. So initial, begin, and in will also be talk much on next one. Just let's consider about these things. So string is written off and example here. So identifier is here. Identifier is actually how to define any variables and how to write or how to declare the different type of variables. Like we can have underscore before the variable name, or differentiator separated by underscore, and we cannot have like spaces in between the variable name. So this is the case sensitive and space must not be there. And this is the very basic example. We will write the standard identifier writing example in the upcoming session. So we can utilize underscore, and we can have one number on alphabetical characters like underscore or dollar. And let's see about the logical value set. So we will talk about the x and z value. X is unknown, z is high impedance floating point, and we can have 0 and we can have 1 value. Logic 0 for 0 and logic 1 is for 1. So there are other things we need to know is like types of data types. So it can be nets consist of wires and this type of war try and etc. So most prefer or utilized net is wire. So we have wire abc, wire multibit, and the another multibit wire that is written up msb is to lsp, and like msb 0 lsp 7. So this can be written up differently or in multiple ways. And wire sign, which is sign type of wire, so it is 8-bit sign wire. So this is the different example of writing or declaring the wire. And there is we have registers. So registers is explained here.